We want to build on now to work we did in the 2 unit course on rates of change. Now remember, the idea of the rates of change is that we're looking at the derivative of something. So in the 2 unit course we looked at the rates of change and the idea that the function was in terms of time. So it was pretty limited in what we did because the function itself didn't change out of a variable of t, and we just did it in terms of time. Now what we want to do is deal with harder functions and more than one function at times. And to do that, we're going to use the chain rule. So be wary that the chain rule is going to be used a lot. Chain rule or function of a function. So because there's going to be more than one function involved. So we'll give us some examples here. You've got a side of a square. It's increasing at a rate of 0.5 centimetre per second. And from that, we want to find the rate at which the area is increasing. Well, so we're told something about the side of the square increasing at a certain rate, but then we want to find the rate of the area. So we have to manipulate, because when we're talking about the rate, we're still talking about something in terms of time. So the idea here is that the side of the square is increasing at a rate of 0.5 centimetres per second. So the derivative then of, that's really meaning the derivative of the side of the square is, with respect to time, would be a half, because we don't know what the actual value of the side of the square is, but we know it's increasing at 0.5 centimetre per second. So that's where we can write the SDT is equal to a half. What we do want to find is the rate of the area that's increasing. So we want to find the dA dt, so the rate at which the area is increasing at a particular value when the side is equal to 8. So we're using ds dt, but when s is equal to 8, we want to find the a dt. So it relies on us getting an expression for the a dt. Now we do know that the area of a square is the side squared. So we could get an expression there and say dA in terms of ds could give us an expression 2s. So we were able to find the rate of the derivative of a with respect to s. So we've got a relationship there. We can also use that, keep that in the idea of the chain rule, where dA dt could be written as dA ds on the SDT. Because we know what the SDT is, that's a half. We know dA ds would be 2s, and when s is equal to 8, we're able to do that substitution. So 2 times 8 times the half gives us the area increasing at a rate of 8 centimetres squared per second. So there's the idea of using the chain rule and being able to get that expression. So let's have a look at another example. This time we've got sides of a cube increasing at 2 centimetres per second. What does that mean? Well, it means that we could write ds dt as 2. And we want the volume, the surface area, and the length of the diagonal. They should all be increasing. We want their rates there when it's equal, when the side is 10 centimetres. Okay, so we're looking at the idea dv dt would be dv ds on the SDT. Well, we got the SDT, but what we want is dv ds. So we know the volume would be the side cubed, or dv ds would be 3 lots of the side cubed. So we can get our expression now for dv dt in terms of s as 3s squared times 2. So we've done a substitution, and we know what s is going to be, so we can do our substitution there. There's our rate of change of our volume as as the side's increasing. Again, if we want to find the area, we want dA ds times the SDT. And the whole idea, we keep putting the SDT in as 2, and this time we've got a is equal to 6x squared, so 6 lots of the side squared, so one side of the cube is s squared, and then we've got 6 of it. Our derivative then would be 12s, so we can do our derivative, substitute our 12s in, and then substitute 10 for s, gives us the 12 times 10 times 2, gives us 240 centimetres squared per second. And then our length of our diagonal this time would be, if we have our diagonal of our cube, relies on us getting dd dt, which is dd ds, over times ds dt. Again, ds dt is 2. But we want an expression for the derivative of the diagonal in terms of s. So thinking about our cube, we've got s times s on the bottom, which gives us diagonal of the base, which would be root 2s, with the height being s as well. Again, we can apply Pythagoras' theorem to get an expression for d as root 3 of s. So there's our calculations. We get root 3 of s. So the derivative of the diagonal with respect to s would give us root 3. So as the s is increasing, and s would increase at a constant rate, so should the diagonal, because it's only a length as well. So that's where we get the root 3 times 2, which gives us 2 lots of root 3 centimeters per second. This time we've got heat being applied to a circular plate, and as it expands uniformly, the radius of the plate is 20. When the radius is 25 centimeters, it's increasing at 25 millimeters per second. What's the rate of increase of the area at that time? Okay, so again, to find the area, the rate of increase of the area would be dA to t. But we haven't got anything in terms of time. We've got no expressions in terms of time. So we need to rely on our ideas, so we know that we can get the radius, the area in terms of the radius, because we know a is equal to pi r squared, so we can get dA dr. And we do know that the radius is increasing at 2.5 centimeters per second. Notice we've gone to the same units. We could change it whichever way we like, but we'll go 2.5 centimeters per second. So dA dr then is 2 pi r times 2.5. So we've done our substitutions there because we've got our expressions that we need. And then when r is 25, we do our substitution and clean it up to get 125 pi centimeters per second. So notice we want the rate of change, and the rate of change is always in terms of t, but we haven't got an expression for a in terms of t, only a in terms of r, so we have to do that manipulation. We've got a spherical balloon being deflated at a constant rate of 10 millimeters per second. So notice this time our radius with respect to time, the rate of change is decreasing. So we put a negative in there. It's going to be a negative. So calculate the rate of change of the volume when the radius of the balloon is 100 millimeters. So again, we want the rate of change of the volume, dV to t. We have not got an expression in terms of the volume in terms of time. In the 2-unit course we would have. Extension 1 we don't. So dV dr this time we can get, because we know the volume is 4 and 3 pi r cubed, we can get dV dr is 4 pi r squared. So we can get an expression for that. And we know that we've got dr dt, so if we can get dV in terms of dV dr, then we know we can use the chain rule to do this, have this expression. So we get the 4 pi r squared times the minus 10, we do our substitution, and we know that when the radius of the balloon is 100, that's what we're hopefully going to get our rate of change of the volume. So we put 100 in, we get 4 pi times 100 squared times minus 10, gives us minus 40,000, 400,000, sorry, pi millimeters cubed, because we get 5, it should be 40,000, because there's only four zeros there, 1 0 there, so we should get 5 zeros, 1 2 3 4 5. There we go. Oh, that we left a 0 out there, so it is 400,000 pi millimeters cubed. So it's decreasing. That's what the negative means in this case. It means it's going to be decreasing. And then we've got a spherical bubble expanding, so the volume increases at a constant rate of 70 millimeters cubed per second. So this time we've got dV to t. So dV to t is 70. So we've got the rate of change of the volume. Now what we want is to find the rate of increase of the surface area. So what we want is dA dt. Now the idea with dA dt, we can get dA dr because it's a spherical bubble, so we know the volume is 4 on 3 pi r cubed. We know, which we know we can get a rate of change for the volume in respect to r. We also know the surface area is 4 pi r squared, which means the ADR would be 8 pi times r. So this requires us to do a little bit of manipulation, because we know dv dt can be written as dv dr on dr dt. So we can get dr dt as 70 on 4 pi r squared. So dr dt, we can get dr dt from that volume expression. So it takes some manipulation of the chain rule there to get the 70 times 4 pi r squared, because we can then apply the chain rule here, which is 8 pi r from what we just did here. And then we can get an expression in terms of r for dA dt. And we know when r is equal to 10, we can substitute that in, and we get 14 millimeters squared per second. So that's really relied on us using the chain rule twice to solve that problem, which is not easy. That's a little bit of manipulation. We had dv dt, we wanted dr dt, but we could get dv dr, so we could get that manipulation. So we could get a function for dr dt, and we could get dA dr, and then substitute that in. So be really careful. You've got to understand what the problem's asking you to do, what does it want, but then also what data have we actually got, and how can we manipulate that to get what we want in the question.